Okay, so today's lecture is going to be fun. It's also going to be very short. The chapter in the book on the discrete Fourier transform was like a little bit too long for one class. So instead of like messing with that, we're just going to have two sort of short lectures. So we'll probably get done relatively early today. We're going to talk about the discrete Fourier transform, something that we've talked about in detail just a little bit already in the sort of the old version of the course. And now we're going to kind of see how it goes, how it gets put together in Python. And then the PowerPoint Design AI was kind enough to give us this video background. I assume that this means that like it's saying like the Fourier transform is the boat that we will take on our journey towards signal processing, I think. That's what's going on there. Okay. Metaphors. All right. Today, we're going to kind of just set up the problem a little bit. We're going to do essentially what we already did with the discrete cosine transform, which is we're going to set up the synthesis problem. Next time, we'll set up the analysis problem and see how the discrete Fourier transform sort of makes that work. But today, we're just going to set up this concept of complex exponentials and then do the synthesis problem in Python. And again, do it with matrices, kind of like we did before. So let's just go ahead and dig right in. Like I said, this is going to be pretty quick. Complex exponentials. So one of the more interesting operations in mathematics is the generalization of an operation from one type to another. What does that mean? For example, a factorial, right? The little exclamation point operator is an operation that only works on integers. So a factorial only operates on integer. The factorial of n is the product of all integers from 1 to n. But, and here's where it gets interesting, what if you wanted to calculate the factorial of a non-integer? What would sort of, I don't know, 3.27 factorial equal, right? How would you calculate the factorial of a non-integer? This is where complex exponentials comes in. So a little bit of history just for fun. In 1730, this guy, Leonard, which is a fun way to spell Leonard, Leonhard Euler, developed gamma functions which calculates the factorials of non-integer numbers. He also gave us the complex exponential function. He also gave us Euler's constant, which nobody seems to remember, but we'll talk about that in a second. The natural definition of an exponential is this, right? So, oops, she's typing a question. The same guy, one and the same. Euler was like he was kind of a big deal. He did a lot of crazy stuff. He was very into math and got a lot of cool stuff named after him. But yeah, so let's go to this. The natural definition of an exponential is, you know, a value raised to some power is the same as that value multiplied that many times, right? So phi to the third is phi times phi times phi, right? That's basic sort of high school, junior high algebra kind of stuff, right? But of course, this doesn't work for non-integers, right? What is you know, phi to the 3.2. What does that look like? Someone's going to say you divide, and you would be mostly correct. But let's move on from that. So using Euler's constant, which is E, exponentiation can be represented as a power series. Think back to Cal 2, right? And actually to this class, we already messed with some power series stuff, right? So e to the phi is equal to 1 plus phi plus phi squared over 2 factorial plus phi to the third over 3 factorial, on and on forever. And this works with imaginary numbers as well. So e to the I phi is equal to 1 plus I phi minus 2 over 2 factorial, minus phi to the second over 2 factorial, plus 3, or phi to the third over 3 factorial, and so on and so forth. But the interesting thing about the imaginary one is that since it's, you know, I is equal to the square root of -1, what happens is we have a negative and a positive, and actually this guy should be a negative, all right, then a positive and a negative and a positive and a negative and a positive and a negative, right? Forever causes it to oscillate. this is fundamentally why we use imaginary numbers to represent sinusoids, is complex values, right? So this is Euler's identity. Who knows? Maybe he wasn't that big a deal. He was just really passionate about putting his name on stuff. So Euler's identity says that e raised to the I times phi is equal to cosine phi plus I times sine of phi. Just a little bit of fun mathematical background. Because of Euler's identity, we can represent our signal at any point as a complex exponential. Right? We can say e raised to this whole quantity, a plus I phi, is equal to e to the a times e to the I phi, because exponents add, is equal to a times e to the I phi, where a is the amplitude and phi is the phase angle. Right? Now notice that this is just at any sort of random point. If we want to sort of turn this around, let's go back real fast, and say that we have, you know, a times e to the phi t, then we get a sinusoid function. So it's a little bit of Python. So Numpy provides us a version of Euler's constant that works with both real and imaginary number. So for example, we can set a value phi equal to 1.5 and then say that our complex number is equal to np dot, you know, times exponent. So np dot exp is equal to, it's like saying e to the that stuff, right? So we're saying ij times phi is going to get you this complex number in rectangular form. So the big take home there is that Numpy provides us a function for working with these complex exponential values. We can also use Numpy to get the real and imaginary components as well as the magnitude and phase angle. So if we take that value z, which, what was it, 0.0707, 0.997, so 0707 plus 0.997 j. Ooh, also, by the way, notice that Python must have been written by somebody who leans more electrical engineering. So Python uses j instead of I. So if you give it a j, it's going to know what to do with it. So 0.0707 plus 0.997 j, right? If you give it, or if you ask for this property of that complex number, you'll get, you know, 0.07. And you ask for the imaginary property, you'll get that 0.997. You can also ask for the absolute value, which will give you 1, or just np dot absolute. In both cases, you're going to get a 1, and the phase angle equal to 1.5. So this is the same as saying a e to the I phi, where a is equal to 1 and phi is equal to 1.5. So e to the, j times 1.5 is what we've got going on there. So these functions, so the property is real, an image, imag, and then grabbing the absolute value gets to the magnitude, and grabbing the angle gets you the phase angle of that complex number. All right, that's it for complex exponentials. Just a little bit of background, not a whole lot that you need to really hold on to there, just be kind of aware of the pieces there. Are there any questions about this complex exponential business? Like I said, the big take-homes are we use complex exponentials to represent sinusoids, and Python provides some pretty easy, or Numpy specifically provides some really easy functions for dealing with complex and imaginary numbers. You know, a example test question here might be, how would you use NumPy to calculate the phase angle of a complex number? And you would say, well, I guess you would select the answer choice that says np.angle, z. Stuff like that. All right, complex signals. So we already kind of alluded to this, but now let's make phi a function of time. So e to the I is now e to the I phi of t, which gives us Euler's identity. Still Eulers. Cosine is a function of time, and sine of phi is a function of time. If the frequency is constant, we have a complex sinusoid, which is to say a sinusoid that has a real and an imaginary component, right? So we have a real component. Whoa. And an imaginary component. In this case, for a sinusoid, they're a function of time. We can simplify it a little bit to just say I times 2 pi frequency times t, where f, of course, is the frequency, and t is the time. All right, cosine of 2 pi ft plus I sine of 2 ft, or sine of 2 pi times f of t, gives us that complex sinusoid. Okay. Think DSP handily provides us a class that implements a complex sinusoid. Then it looks like this. Class, complex sinusoid, def, evaluate, t of s. So phases are, it's kind of like what we saw here. We've got 2 pi times f times t plus some offset, some phase angle. Notice that the only difference here between, this and class, sine signal, is that one, y of s is a function of np dot sine, whereas this one is a function of np dot exponential. So here we're saying that ys is equal to a times e to the j phi, and returning that. So we're returning a complex number as opposed to just a basic sine function. So that's the important difference between the complex sinusoid and the regular sinusoid. And so, for example, if we were to plug this into Python and say signal is equal to think DSP plus complex sinusoid, frequency of 1, amplitude of 0.6, offset of 1, we're going to get, and make it a wave, you'll get your y's that are all just these, comma, right? A list of complex numbers instead of just a list of direct real y values. So, any questions about the complex sinusoid function that ThinkDSP provides? Why it's important to use complex numbers won't be apparent today, but we'll get to it when we finish up this discussion on Wednesday. So let's talk about the synthesis problem. So the synthesis problem is exactly the same as the one that we saw with the discrete cosine transform. So just as with real sinusoids, we can create compound signals by adding up complex sinusoids with different frequencies. So here's our complex synthesize function. And the important thing is here, right? So our components, just like before, remember we're putting those pieces together of our frequency components. If we know the amplitude and we know the frequency, think DSP dot complex sinusoid now passes the frequencies and the amplitudes for amp and freak in zip amps dot freak, right? So we're iterating through that for loop, grabbing all the components and then just sticking them into a complex sinusoid and creating a list of complex values. Then we're summing them together and evaluating the whole thing. So exactly the same as our original real synthesize function. The only difference here is that we're using this complex sinusoid method. And if we take a look at it in practice, amps is equal to this array, the same values that we saw with our DCT functions. Frequencies, we got our frame rate, 11.025 kilohertz. We create our lens space, and then we synthesize our y's and get this business. And if we want to plot it, we can plot the real and the imaginary components separately. So we can lay them over each other. And here's what that's going to look like. So let me go back and say first we have just the real. Here we have the imaginary. We're grabbing each of the y's components, but we're grabbing that, IMAG, that imaginary property, and here we're grabbing the real property. So we're plotting both of these guys on top of each other. And here, take a look at it. And it's pretty cool because if you notice, that real component is exactly the same that we got when we did synthesizing when we were talking about the DCT, right? It's the same real synthesis. The only difference now is that we've got this imaginary component that is a little bit different. It's hanging on and sort of coming along for the ride. So we can think of it in broad strokes as this is giving you the amplitude of your function, and the imaginary component tells you a little bit about the phase angle of your signal. So when we synthesize this function, we get two components, a real component and an imaginary component, and when we plot them against each other, we can see that the real is exactly what we expected. It looks exactly the same as what we had before, but the imaginary component is a little bit different looking. So, any questions about that synthesis? Okay, cool. All right. Last up, let's talk about synthesis with matrices, right? So we need matrices to sort of speed things up a little bit. Just like with our discrete cosine transform, we can use matrices to implement our synthesis function, and we can do it a little bit more efficiently. So here's what that's going to look like. Our synthesize 2 function, same deal. We're taking amps and frequencies, and we got times. We're calculating that outer product, T crossed with our frequencies. And the only difference now is instead of using our sinusoid function, we're saying np.exponential. So now we're saying we want a times e to the j 2 pi of t outer product with f of s. Just like that, and we return the y's. So if we give it a shot, we do synthesize, we'll get the same values that we got before. And if we do it all and go to plot it, we'll get a function that looks mostly the same. Let's roll it back just a little bit though. I want to see, was that up, down? What's changed? Notice that the real component is approximately the same, right? It starts up here, it was 1, comes down, but then our phase originally starts, our imaginary component really starts at 0. Yeah, the phase is shifted over a little bit, right? And if we go and take a look at our new one, the real component stays the same, but notice that it didn't get shifted, it got inverted, right? It started at almost, well, I guess you could still call that shifted. But it basically says instead of starting at 0 and going up, like it did before, it's flipped over. It starts at almost 0, and it's coming down and trickling back up. So doing it that way flips the phase angle, which isn't really a problem since our function is periodic. And so which means it's going to be symmetric about sort of a center point in the phase. So that's the only take home there, is when you do synthesis with matrices using complex values, you're going to get a phase shift that gets flipped over just a little bit. So I think, and that is actually it, man. It's only 20 minutes. So I told you today it was going to be pretty short. Maybe we could have fit the whole thing into one lecture. Done a lot faster than I thought it would. So just to recap, we talked about complex exponentials. Yeah, I didn't think you would mind too much. Complex exponentials, talked about complex signals, talked about how to do the synthesis problem, and then how to use matrices. And the big thing there at the end there is that matrices causes the phase to flip over. So are there any questions, comments, concerns? That was lightning fast. We will pick up the back half of this lecture on Wednesday. It'll probably also be about as short as this. But if there's nothing else, that's all I've got for you guys today. Nope, no homework right now. Maybe on Friday when we finish the chapter.